Recording on. Good. Excuse me, still my coffee. Okay, so what do we have here? This is where we were yesterday. To step back a little bit, I was working on an example, which I did finish, in fact, about the computation of center manifolds. Remember why we're looking at center manifolds, because they are critical, really important near non-hyperbolic fixed points. And an argument would be, why would a fixed point be non-hyperbolic? Why would I have eigenvalues of 0 real parts? I can have so many other real parts, and it's a perfectly legitimate argument, except that it so happens that when you have parameterized families of models, almost inevitably you're in a situation that for some values of the parameters, as your system deforms, you will be losing hyperbolicity. And again, just keep in mind the steam engine before we dismiss the importance of that's exactly what happened there. There's an equilibrium point. People were changing, which was nice and asymptotically stable. People were changing the parameters, and it was okay. And it was okay until it was not okay. And that's exactly underlying the importance of understanding of what happens at non-hyperbolic fixed points, to be aware of them and see what happens locally near them. Also, I perhaps didn't say, but some say very weakly damped oscillators, damping coefficients of steel are very small. So you have an oscillating beam. Many other structures, lightweight structures, they can oscillate for a long time before they really settle down. What does that mean? It means that that equilibrium point that you're looking at ultimately is almost like a center point. It's a very small perturbation to that, right? So you're always kind of near criticality in terms of hyperbolicity when you have a weakly damped, very weakly damped oscillator, right? Because that tiny damping is the one that puts you away from being non-hyperbolic for the fixed point, like a center, which oscillates forever. So who knows what you're creating with the introduction of tiny damping and perhaps additional forcing, and indeed interesting things can happen in weakly nonlinear oscillators as a whole subject by itself. So they are more ubiquitous than one would think. So in that vein, we have been looking at center manifolds, and we got to the point that you can look for them once you have partitioned the coordinates into this block diagonal form. You can look for them using the fact that they are quadratic graphs over the center subspace. Excuse me. And then that idea led to this invariance equation, which is a nonlinear PDE for the center manifold. But we had an issue that we didn't quite have boundary conditions for it, because we just didn't know what to say about the center manifold over here. I mean, we have no idea where it is. We cannot pose a proper boundary value problem for this PD, and this other point is not a boundary for the domain. It's just an internal point, okay? So instead of that, we went for a Taylor expansion. So you can look for the center manifold in the form of this expansion, and what comes to your help is that you know that it's 0 at 0, this graph, and also it's flat at 0, so this term is also out, so you start with quadratic terms. And that's really the main principle. You then plug that into the equation and determine the shape of the center manifold. Once you have the shape of the center manifold to some level of accuracy that you're targeting, you can take that shape and plug it into the X equation that you had. Remember this equation in the decoupling, because a motion on the center manifold is enslaved to the X variables. Once you understand the X dynamics, you can just lift it up to the Y dynamics simply using the graph, this formula that you have for the center manifold, correct? So once you understand this, that's enough. So that's a fantastic opportunity to have a rigorously derived reduced order model, just by whenever you see Y in the X equation, plug in H of X, okay? And that gives you a mathematically well-defined reduced order model. Now, is that also relevant, although it's well-defined? To keep in mind that if you have any invariant surface, of course, you're welcome to reduce the dynamics to it, but is it going to be all that relevant for general initial conditions? And the answer is only if that surface also attracts other trajectories, which will then in turn synchronize with your reduced dynamics. Now, that is the case if there were no unstable directions to begin with. there are in fact applications in which, even if you have unstable directions, so therefore this center manifold that we're looking at is in fact a saddle type surface potentially. Along some directions you're approaching it, along some of the directions you're leaving it. There are cases in which, despite its instability, it will play an important role, and you still want that reduced dynamics on it. But in that case, I wouldn't call it a reduced model, right? Because your general trajectories, the idea of model reduction is that, you know, it should work at least in part of the phase space for any initial condition. So you're reducing that large equation that you had, at least in part of the phase space, into a smaller set of equations. But this only works as a reduced order model if it's really relevant for all nearby initial conditions, so it has to be attracting. I did an example then. This was already set up in a coordinate system so that we didn't have to do additional block diagonalization. The x equation was aligned with the x-axis with the center manifold, the y-axis with the, or center subspace, y equation with the decaying direction, a stable subspace. This is what we had under linearization accordingly, right? These are the stable directions. And then I went ahead and, you know, plugged in the formula for the center manifold. Mind you that it starts with the quadratic terms, and you can go up to any order that you want in terms of precision. And then there was this key idea which led to the formally to the derivation of that invariance PD. You either remember that PD, which I don't reckon. After all these years, I can reproduce it pretty quickly, but the way I reproduce it each and every time is that basically very, very quickly rederive it. It doesn't cost too much. And while at it, I can actually then use the particular shape of H that we are assuming. So rather than rederiving the PD and then starting to plug in on the fly, I already plug in H of X, right? How do I go about that? I take the relationship Y equals H of X, and I simply differentiate it with respect to time. And I'm allowed to do that because here's the idea that this is more than just a single point relationship between points. It must hold along full trajectories for all times. Therefore, I view this as a function of t, and I view this as a composite function of t, and I can differentiate both sides, and that's what I did here. Okay, and then I just omit the time dependence in my explicit notation. Gradient of H, or Jacobian of H, just H prime because X is one dimensional. So we went through this calculation and compared sides of the two polynomial expressions on both sides, and that actually always leads to linear systems of equations. This problem is always solvable, luckily. That's just the nature of it. And you recursively go, you know, first solve low order, higher order, even higher order. And then we get this expression for the shape of H of X, quadratic parabola, depending on the sign of alpha, and then inverted quintic parabola. And then there were two cases, right? We looked at. In one case, this uncovered the saddle point. On the other one, it uncovered additional stability. So really, depending on alpha, the dynamics in the center manifold was either stable or unstable, but that required truly nonlinear analysis. This didn't come out from linearization. And indeed, what decided about the stability was in fact a nonlinear term right here. So linearization would throw its hands up in the air at this point and say, sorry, hyperbolic fixed point can't help you out. You just have to do really truly nonlinear analysis, which we did here. It also then, two things, we also learned that this is not the end of the story, because if you then restrict the dynamics, then it can, away from the origin, when you cut it, then you might be ignoring terms that are just as important as the terms that you're paying attention to. That's not going to happen at the origin, because at the origin, any lower order term is infinitely stronger than any higher order term in the limit. But as you start making statements about, say, fixed points of this one, of this part, which actually it will have two here, okay, then you're at a finite distance. Look, this distance was finite, 1/2 alpha. And when you're at a finite distance, then this term may be equally important. So that's one question to keep in mind that I'm going to come back to. And the other question is that how relevant is all this? Because when I add even just a tiny perturbation, epsilon times x, right, then the linearization, depending on the sign of epsilon, either gives you a stable fixed point, asymptotically stable one, right, when epsilon is negative, or a saddle one. When epsilon is positive, this direction grows and this one decays. So tiniest change, center manifold is gone. Was it a complete waste of time to deal with the center manifold? And luckily, no. Second. Any questions so far?
I have a quick question, if I may.
1 second, I need to ramp up the volume. Okay, go ahead, Ahmed.
Yes, you mentioned yesterday that we can do the same also for the stable manifold. So we
Correct.
can also block diagonalize, I think the, well, its bases, and the other block diagonal would have the center and the unstable subspace, but only then yes, it won't be useful because we cannot do any lifting, right? Since the trajectories will never collapse and like leave the center manifold into the stable manifold, right?
Let's just go back to the picture so that I understand better. It's actually, here's an example, right?
Yeah.
Here's the stable manifold. In general, we would not be so lucky that it persists as a line or subspace. We would have a stable manifold, generally speaking, like this, right? Something like that. Okay. What I meant is that you can still look for this stable manifold. You would then view all the remaining variables, the center and the unstable variables, as functions of the stable variables, right?
Okay.
So then you would do a re-block diagonalization, if you will, where you would pull out the stable variable, a stable subspace, and over that you would be constructing a graph whose dimension is equal to the number of stable directions, right? And you would be enslaving the remaining variables. You, in some same procedure, but theoretically you're better off in the following sense, that the stable manifold, at least the fast stable manifold, is unique, because as you may have seen in this example, the center manifold may actually add further slower directions to the stable manifold. So technically speaking, the stable manifold turns out to be, for certain values of alpha, is a whole open neighborhood, or just turns out to be what you had. So technically, what in these examples, what you can really uniquely continue is the fast stable manifold, which is always unique. This is a new term that I'm just using, throwing this out. In part 2 of the course, I talk a bit more about those, but it's basically, it's for cases like this. Generally speaking, it turns out, just sort of a preview, that if you have a stable manifold, you know, lots of stable directions, suppose you start with a stable subspace, then you start picking out just the lower, like so suppose this is the simplest case, right? Where you decay fast here and you decay slow here, all right? So this would be the inside of a stable subspace, generally speaking, which is not just one-dimensional, but two-dimensional. If you look for substructures within that stable manifold, then it turns out that, as I talk about that in part 2 of this course, the slow ones have the same type of non-uniqueness in general as the center manifold. And you see that very clearly, that the way to complete this picture is you turn that, well, this is a node, right? And you see immediately that if you, even in the linear system, there are infinitely many other slow stable manifolds that have the exact same property, that they are tangent to the slow stable subspace. And that generalizes more actually to higher dimensions. This can be of arbitrary dimension. I just pick out a few slow directions that are slower than anybody else, and I separate them from the rest. If I want to continue them within the stable manifold, then I will get those submanifolds, but there's no uniqueness. The opposite is true for the fast ones, just like this one. See how unique it is in this sense, that there's no other trajectory that is tangent to this direction at the origin, that generalizes to higher dimensions. If I grab the fastest 5, 6, 10 directions within a stable manifold, and I call that the fast stable manifold because it's faster than the rest, that turns out to have a unique continuation in this sense. So this is an interesting duality. it just so happens, unfortunately, or fortunately, who knows, for your purposes, but it's always the slow directions that really matter for model reduction, because you're coming close to them, right? And for those, you don't have a unique continuations, because the fast ones, see, in a case like this, oh, it's the other way around. The fast directions, even though they have this appealing uniqueness property, they are so atypical for the dynamics that even though I can technically restrict to them, if I use it as a reduced order model, I'm misleading myself, because the general trajectory will not experience that fast decay to the origin, but rather that will be a transient in its behavior. And then its dominant behavior, long-term behavior, will be really small, slow decay, right? So what I get from the fast stable manifold, however appealing it is to work with a unique manifold and restrict to it, and that's perfectly fine. Unfortunately, that restricted dynamics will not be a good reduced order model in general. But that's just a long-winded answer to a much simpler question that you asked, I think. Anyway,
yeah, thanks
did I answer your original question?
Yes, even my question wasn't very clear, so that was quite the reply. So
I think okay, no, I think it was clear. Okay, anything else? Let's then move on. And what did I want to do? Yeah, well, the last question, this rhetorical question, was, and anything remains, and hopefully you anticipate that I didn't just do this in vain, and it does have some, obviously has some significance. That expectation turns out to be true, and the construct that is born out of this expectation, so this whole next subject is center manifolds depending on parameters. And that brings us a whole lot closer to reality, because all of a sudden we're not just looking at non-hyperbolic fixed points, but we're asking the questions. The question, we found really interesting things for non-hyperbolic fixed points. Do these things have then any implications for nearby dynamical systems that technically no longer have non-hyperbolic fixed points, but they're very close to whatever fixed point they have, very close to being non-hyperbolic. So the setup accordingly is the following: that you have still a splitting like this that we have already achieved, but I'm now allowing for a perturbation in there by epsilon. And it will be important what the form of that perturbation is, some general knowledge dependence on epsilon. And I'm getting to that now. So X is still C-dimensional, so it's the center directions. Y is still D-dimensional, okay? And this epsilon that I'm allowing now is just a general P-dimensional parameter. So it doesn't have to be just a single scalar necessarily. It can be multiple parameters that somehow perturb you away from that limit. If you have a general physical system, then your epsilon will not be whatever the Reynolds number generally or the density, but rather its deviation from the critical value for which you got a non-hyperbolic fixed point, right? So the way to think of epsilon, because it's a small parameter, so in norm, it's going to be much less than 1 or 0, that it describes deviations from a parameter setting for which you got a non-hyperbolic fixed point, right? So say Reynolds number minus Reynolds number critical, length minus some critical length, or mass minus your actual mass minus some critical mass for which you had this degenerate fixed point. And here comes the crux of the matter. So these f and g are functions, they used to be just at least quadratic functions. So this doesn't mean, right, that it's exactly quadratic, but it's big O x squared, so quadratic or higher. So they can have terms like this, and they can have products of norms of these, so like bilinear terms, but that doesn't preclude you from having x to the 5th or x to the 7th and so on. Plus, nobody says, right, that these have to be just polynomial, just to clear this up, right? I mean, it can be any function, but I'm making a statement about the Taylor expansion of that function near the equilibrium point. I know that the function vanishes at the equilibrium point because the whole system has an equilibrium point. That's my fundamental assumption. And for this analysis, the type of analysis we're doing, local analysis, what really starts mattering is not the full shape of the function because it's a local analysis still, but it's Taylor expansion. Behavior is Taylor expansion. So it's not just polynomials that matter clearly, right? But it's just when I be big OX, I'm trying to be very general, and that can be just what? Sine squared x that expanded right there, right? So that's order x squared. Okay, and what the new feature is that I'm also allowing epsilon norm times x norm and epsilon norms times y norm. So what is that? So what I allow is changes from my critical configuration at which I had non-hyperbolic fixed points. So I still have that the spectrum. How do I write this? The imaginary part of the spectrum of A, that's kind of shorthand notation, is 0. Okay, and the imaginary part. This is kind of a little bit sloppy notation, but you understand, right? We went through this before. So these directions, the eigenvalues of this matrix B do not lie on the imaginary axis, whereas all eigenvalues of the matrix A lie on the imaginary axis, including the case, of course, when those eigenvalues are 0. Okay, so it's the same partition. But my center of analysis is still a fixed point at the origin. So xy equals 0, 0 is a fixed point for all epsilon. Okay, because then you plug in xy equals 0, then this still vanishes and that vanishes. Okay, but these terms, which I list as quadratic in epsilon x, could easily and generally will be coming from a perturbation of the linear part already. So again, you can have higher order powers of these as well, but at least they have to be of order epsilon x, and that means that already they are occurring at the level of the linear system, right? Because x and y are linear, but I have pulled those out of the linearization and put them here, that for reasons that will become clear shortly, right? So this is not just a higher order perturbation to my critical system. It's my criticality. It's actually already I'm perturbing the linear system. Now you might ask that why don't I also allow for terms of order epsilon squared or even order epsilon, right? And that would be a good question. And we spent time on that before. Of course, yes, a general perturbation to the system could be just constant, right? I'm just shifting, I'm just adding a constant to it, or I'm changing a constant in this equation so that it's just hanging out there by itself. The only thing to remember when we potentially talk about that is that this is now a non-hyperbolic fixed point, and we have a non-hyperbolic fixed point. Then if we add a perturbation that kind of removes that fixed point right there, then it's not a priori guaranteed that the fixed point survives. I would have to, we did go through this before. We looked at the implicit function theorem argument, and what we concluded is that we can only guarantee the survival of a fixed point under this general order epsilon perturbations that do not vanish at the fixed point if the eigenvalue, if the matrix linearization has no 0 eigenvalue. And I don't want to exclude that case now because I'm looking at non-hyperbolic fixed points, okay? So a priori, I don't want to exclude the case of 0 eigenvalues in here. If I don't exclude the 0 eigenvalues in here, then there's no guarantee a priori that if I add an order epsilon or order epsilon squared perturbation, which can just be as simple as epsilon itself, there's no guarantee that the fixed point survives, okay? That's why. Now, if there's a way I can guarantee that, because either, I make that as a note here, okay, note. If the fixed point is known to survive under, say, purely order epsilon squared, and I should write that in norm, perturbations, which means, for instance, this is just an example, A has no zero eigenvalues, because then the implicit function theorem applies. We discussed that before, and we can then conclude the persistence. Oh boy, this is hard to read even for me, so sorry. So A has no zero eigenvalues. Then what we can do in that case, then I can actually allow such a perturbation, order epsilon squared perturbation, and then simply then note that I have a surviving fixed point, which is, I'll just write it out. I used to have 0, right? And now there's 0 plus order epsilon squared. And then I simply introduce a new coordinate x tilde, which will be the deviation from that x epsilon. So basically what happens is that as epsilon varies as a function of epsilon, I'm remeasuring, I'm redefining my coordinate, always from the persisting fixed point. Okay, so that persisting fixed point by this change of coordinates will be always at 0. Okay, and that then in the new set of coordinates removes that additional order epsilon squared term, and I'm back to this type. Okay, so for that reason, if originally my system also had order epsilon squared here, then I wouldn't have to say, wait a second, I can't really apply this whole theory. Then I just have to take a second look. And if I find that either A has no zero eigenvalues, or in some other way, the system has a symmetry, so I can guarantee that even though A has zero eigenvalue and the formula of the implicit function theorem doesn't apply, I can guarantee that somehow that the fixed point survives, then I simply pass to a new coordinates in which the fixed point just is stuck. The surviving fixed point is stuck at 0, right? And at that point, precisely because it's stuck at 0 for all values of epsilon, this form becomes relevant, okay, in the new coordinates, okay? So then, the dynamical system becomes of the form above in the x tilde variables. Okay, so then it's no loss of generality, but I have to have that additional assumption. Okay, I'm just noting that here on the side so that you don't think that this is overly restrictive. Because indeed, why would I not have just a constant perturbation, right? I mean, sure, but then I need this extra assumption. Okay, so other than that, I mean, the setup is clear, and this is the essentially the only difference, right, from what we had before. Okay, but we didn't have these terms before, right? And technically, if I look at them the old way, then when I add these in my usual treatment, these terms would actually belong here. The minute they belong here, they upset my stable and unstable subspace designation. They upset the coordinates that I have chosen, and so on, right? Because they detune me from that critical linear setup that I have assumed. Now, I'm setting myself up, hopefully, for a trick so that I can avoid that major upset that all of a sudden removes the center manifolds. Remember this example? This is exactly what happened here. The addition of that term to the linearization removed the center manifold. What I'm doing now, I'm reclassifying this term, hopefully getting away with it, as, well, kind of a, it's an afterthought in the nonlinearity, even though it's technically a linear term. Now, under what is this really allowed? Because the whole center manifold result existence does assume that this is a nonlinear term. That was a fundamental assumption, okay? And now I'm squeezing in a linear term there. So seems like I'm violating the assumption of the center manifold theory. And in fact, on the surface, I'm violating it unless I change my setup slightly, okay? And this is what I'm going to do now. So I rewrite. So right now, the center manifold theorem is not applicable because somebody is cheating here, most prominently myself, right? So I'm just putting stuff there that doesn't belong there. It's a linear term, right? It's the center manifold theorem is inapplicable as is. But I rewrite this existing system in the following way. I introduce now another variable, which actually this is going to be my x tilde now. And perhaps, if you forgive me, I go back because I don't want you to get confused with this x tilde here. So I call that x hat, okay? Because this is a completely different thing that I'm doing now. It has nothing to do with what I did here. So that was x hat, all right? So rewrite this system, which I didn't call anything. So rewrite star, and this is star, okay? In the following way, I'll just write x tilde. This will be a new variable. And before you ask what's x tilde, well, x tilde is nothing else but x, which was c-dimensional. And I'm simply adding epsilon as a dummy add-on to this. We call these dummy variables because they're not really variables, they're constants. Thereby, I'm enlarging x from being c-dimensional to c plus p-dimensional, okay? And then I write x tilde dot equals a new matrix A tilde, x tilde plus f tilde x tilde y tilde. And epsilon, this is now a modified function, which I'm explaining in a second, in fact, right now. So f tilde will be just f and 0. So where did epsilon go? Well, epsilon is now sitting in here. What about the rest? I call y tilde to be y, and I write y tilde dot equals b tilde y tilde plus g tilde x tilde y tilde. So what's g tilde? G tilde is in fact just g. And y tilde is just y. So I'm really not tinkering with the y equations at all, except that now g tilde, maybe I should be a bit more precise here. Functionally, g tilde of x tilde y tilde is the same as g x y epsilon, but these two are now coupled together into a single variable, right? And they are sitting here. And y is just y tilde, so that sits there. This is just basically different notation. Well, it's a notational trick. So let's see, is it correct what I've written here? Because this variable is now enlarged. The y tilde variable is basically what I had before. This is now double star. So there's no change here, just notational juggling. B tilde, maybe that's the only, it's just the same as B. But so there's not much really to say about this equation, but I did change this equation substantially. I enlarged it from this equation. So I changed it. Is that correct, that change? Let's see what I've added here. Since the new components of x tilde are just epsilon, I'm adding epsilon tilde dot here, or epsilon dot here, which I never had here. But I can make an equation for epsilon, right? I can just add this equation here. Epsilon dot equals 0 because it's a constant. So that if I add that equation, I append the x equation with that, I'm not changing anything, right? Now, have I done that? Well, first, in terms of the nonlinear terms, I'm certainly doing that because I'm in the epsilon slot, I'm not adding anything to f. So the nonlinearities are consistent with the fact that this equation is, perhaps I write it closer to, excuse me, I write it right below x. So it's epsilon dot equals 0, okay? So this is what I'm looking at right now. And certainly the extended F has just a 0 there, so no question. But I have to change A accordingly to account for that. And that then tells me that I should define this A tilde to be what it used to be, A, but then write zeros of appropriate dimension here. Because ultimately, I should not have any linear function of x or epsilon here. If I did, I would change the setup. But if I add these and I add that 0, these have the appropriate dimension. This is C times C cross P. So these are different types of zeros, okay? Just I'll leave that to you that we can figure that out. This is a C times P matrix of zeros. This is a P times C matrix of zeros. And this is a P times P matrix of zeros. And then with this trick, I managed to pretend that this is a parameter-free equation. And very importantly, it does have a 0 at 0. Okay, so this x, here's the things to know, that x tilde y tilde equals 0, 0. But mind you, this is now a larger 0 here because it's x tilde is now C dimensional plus P dimensional, right? But formally, it's a 0 for this equation. Just to check that, right? Plug it in, it's a 0. And also, epsilon A tilde is such that the imaginary part of the spectrum of A is 0. Why? Because A tilde is largely A, right? For which this is true. And I'm adding a new block diagonal term to this. And this block diagonal, then the eigenvalues, I can read off what I'm adding here. It's all zeros. So I'm adding P0 eigenvalues to X tilde. So I'm not, the spectrum of A tilde is the same as the spectrum of A plus a bunch of zeros. So the imaginary part of the whole spectrum remains 0. But since I didn't tinker with B tilde at all, B tilde equals B, and therefore the imaginary part of the spectrum of B tilde is non-zero. So I'm in the exact same setup as I used to be when I did center manifold theorem. But I stated the center manifold theorem. So I can actually now go ahead and use apply the center manifold theorem to this funny system that I really just got by adding epsilon as a dummy variable. Okay, so what does that give me? I certainly didn't change the smoothness of the right-hand side by these additions. I really just added zeros, and 0 is as smooth as you want. So this means that with this addition, there exists a not necessarily unique, but there is an extended center manifold, okay, which now, what did I denote this? Well, just like that, of 0. And that is now this, if you want, 0 tilde. So I can add that in the extended phase space, okay? I don't think this is just standard mathematical notation, but hopefully you understand what I mean. It's not the same 0 that I used before, okay? And there is that at x tilde equals 0. I don't like this idea of 0 tilde, so it's just a 0 different dimension. I don't want to be held accountable later that I taught you things that make no sense. So x is just a 0, but what 0 is this? This is C I had originally plus P, right? It's in that space, okay? And it has all the properties that we love for center manifolds. So this is invariant. It's CR minus 1, okay? And it's tangent to what? It's tangent to the extended center subspace, which now contains the directions of epsilon, right? So it lives in this, so just add all these dummy variables, that's additional dimensions to the center subspace. And then this extended center manifold is a graph over that. At what point is it tangent? It's tangent at, now if I write out what this means at 0, 0, okay? And dimension-wise, the dimension of this extended center manifold is the same as the dimension of the extended center subspace, which is C plus B. So this is really just reapplying the classic center manifold theorem to this. What's the advantage of this? Well, the advantage of this is that now, mind you, that I'm making a statement about something, an invariant manifold, that extends across some open neighborhood in epsilon. So not just epsilon equals 0, but now I'm cutting into epsilon non-zero territory, okay? So let's have a picture of that. So sort of to see what this buys for me. So since I'm working in the extended center subspace, I think I choose something like this. All right, so this is then AC tilde. And AC tilde has two notable directions. Here's somewhere the equilibrium point in the middle. And in this direction, it's actually thin, like that. Here's the classic EC subspace. So what you see here is the original center subspace. And then we have the epsilon direction, which runs here. So this is the epsilon axis. Okay, let's just suppose that this is the positive epsilon direction. So this is this extended subspace. And what I'm going to show in the other direction is y. Okay, the y variables. And y is just the same as y tilde. Okay, that I didn't change. And the statement is that in this extended subspace, I have a center manifold for close enough, obviously. This is locally true as the original one. So sort of, I could draw a cup-shaped surface that's tangent here. And I think that's what I did for years without really thinking too much about this. I'm embarrassed to say that I think it was probably at some point, I don't know how I noticed it, maybe a student pointed out to me that this is not quite consistent with what we are assuming. So I give it some thought before I actually start drawing that center manifold. So let's just draw part of it, which you already know. What we know about that for sure, we know that if I take this slice, the epsilon equals 0 slice, right? Then I'm in usual center manifold territory. So there I'm justified to draw that, no question, right? Because at that point, epsilon is equal to 0 in that slice. And then the usual center manifold theorem applies. So let me draw that first. And I'll just, since that's only going to be part of the story, I use a dashed line there. So let me actually try to attempt to even draw this slice. If that works, yeah, it does. Okay, so that's the epsilon equals slice, epsilon equals 0, and within that I'm comfortable, right? Because I know that something like this will exist. I mean, I don't know if it's a quadratic tangency as I indicated, but I certainly know that it's a tangency. And what this is I indicated here, this is WC at 0, at epsilon equals 0. All right, now I have a larger surface here, but that larger surface has to respect the fact that for any epsilon equal to 0, any epsilon equals 0, look at my assumption, the origin remains an equilibrium point. If I allow for epsilon squared perturbations, as I described here, then even after that, I have to shift the origin to 0, right? So again, in order for me to be in this setting, but in this setting, no matter what, epsilon bigger than 0, less than 0, or epsilon is a vector, the origin remains a fixed point, okay? So that center manifold, whatever I have, cuts of the center manifold still have to go through 0, okay? So this will actually be, therefore, under my current setting, is not a general cup shape, but it will more be cylindrical. Okay, that doesn't violate a cylindrical manifold is still in the general class of cup-shaped manifolds, except that in one direction, out of the many over which it's generally a cup, which means tangent to those directions, along one direction, it'll be actually flat. So the way to think about that is that this equilibrium point actually survives, and when I extend this manifold, it will generally deform the extension, right? But it will have to come down now for epsilon 0 and go through this point. And the other thing that I incorrectly drawn, and I'm there as to admit that, because I never thought about that, and I think it's definitely a student that pointed that out, is that there's no reason anymore to think, and I used to draw it like this, that it turns back right there. Okay, that's also not the case. Well, why would it turn back? It just generally goes through. There's no result that would guarantee that this, once I have a cup-shaped manifold, which was, all I know is that the origin is tangent to the, right at that point. But when I extend it, there's no reason to expect that it remains tangent also along that line. Okay, that is not the case. I only know that the tangency is here. So I used to draw it like this automatically. But actually, and you'll see that indeed, when you start looking for it, generally speaking, that's not the case. It could be the case, but that's not by no means, and that has to be the case. So that's why it's a bit more involved to draw in the general case, but I attempt it now. So again, it's a manifold that extends, certainly lives in this extended phase space. It comes down, and I know that it sort of goes down, right? And then it takes this point, and generally speaking, actually goes through that point with some tangency, with some slope, and potentially afterwards then kind of starts turning back, and then re-intersects this. So that very simplified picture that I have drawn for years would actually be possible, but it would be misleading because it would be actually a very special case. So it comes back here and then sticks out. So this goes through that point, but okay. And then of course, then I have to break this there. Do that. So, then I did a whole lot more damage than I intended to do, but that's okay. So where am I now? I'm blue, so I go through that point right there, and then I become visible again. Okay, and then I come back there, right? And again, maybe I work on this a little bit, so it becomes a bit more artistic. So it does have for it to have a cusp there, because I'm cutting it out. So something like that. And then it goes through that and continues over there. And finally, it comes back down at some point. Okay, so this here line continues to be an equilibrium point in epsilon. That's how I set it up. So this is a surviving fixed point. Okay, so what I used to draw, once again, right, something like that, and then moved on. There was a tremendous oversimplification, and in fact, you could not depart from this line under the assumptions that we have, because it would imply, if I also curved up as I move out of that plane, if I curved up, it would mean that the x equals 0 is no longer an equilibrium point, right? But that's not possible by these assumptions. Okay, so let me just label this thing. This is the extended center manifold then, right? So W tilde C at 0. Okay, so that's the surviving fixed point. Okay, and then this also means that the dynamics, you then cannot have, all right, this is about the shape of the manifold, but then can I just wander around this manifold like that? No, because remember that in the epsilon direction, you have actually no dynamics. So to get the any actual dynamics for any epsilon non-zero, this is an invariant manifold, but what's going to be relevant is a cut of that invariant manifold with an epsilon equals constant plane, because you're still confined to that. So I try to draw that now. Hopefully that works. Yeah. Okay. So this would be, say, epsilon bigger than 0 constant. So I would then have to take the intersection of that, and this is getting busy, but hopefully you get the idea. So then I take this plane and intersect this manifold with that. Suppose this is the starting intersection point, and then I get another manifold, which already starts going through with a finite slope here, downwards. Therefore, it technically starts sort of becoming a dotted line here, and then it reaches its maximum and minimum and then starts coming back and somehow lands there. Okay, so this would be then an actual surviving invariant manifold. For epsilon bigger than 0 fixed, right? And then your whatever dynamics you have is taking place on that. Okay, still has to go to 0. Now I'm going through great pain to draw this, but I wanted to point out that this is whoever came up with this idea of doing that was a very smart thing to do, because we're capturing actually a highly non-trivial object here, which continues, which is a continuation of the center manifold, which would normally not be robust. And that we kind of had the extended construct, which gives us a whole lot more big picture. But when you actually have a particular system with a particular fixed parameter, then you're confined to this surface. Okay, so you're not going to be moving in this direction. Okay, any questions on this? I mean, one question would be, all right, but does it make, let me then ask the question, how do we compute this? Does it make any difference in the way we compute it? Yes, there is a difference, because as the computation is only justified by in this setting. Okay, see, you're for epsilon bigger than 0, you're no longer tangent to the center subspace. Okay, technically you have become a weak stable or weak unstable manifold, and you could then do extra work to realign your coordinates with this and so on, right? But can we, in the current setting, go ahead and in fact still calculate an approximation to this surface that I'm showing here. There's some elements of this surface. Still, graphically, it's missing a few things. I mean, you would see a cut here, obviously, going into that plane, right? Surfaces like that, and then it's on the other side, it might join up with that, yeah, uncertain what exactly, and then, you know, at the end it would come down here, there too, and who knows what it would do. So, but certainly this cut you would see here, right? And I was in the right color, right? Until you run into that plane. Okay, that's what we're talking about. So how would we compute it? Of this, you know, actually what I'm really interested in is not the full manifold for given value of the parameter, but actually what I would call W that cut. So W C epsilon 0, because why carry all these directions? I mean, this is potentially a large set of directions. Why carry all that separately in my calculations, why work with this large dummy set of variables, potentially very large? I mean, computationally, that's extra burden. If I'm really just interested in this piece here, and that's what I'm calling WC epsilon, that slice at 0, right? Which is still only has any meaningful geometry in the x directions, right? Because it's constant in the on the y. It doesn't bend in the epsilon direction at all. Okay. So how do I compute that? Well, it's the same center manifold recipe that we have followed. So I'll just say by the center manifold theorem, the classic one. Y tilde, also along that surface, which is the same as y, is h tilde x tilde, which is the extended version, right? But let's write out what that means. It's a quadratic function then of x squared of epsilon x. And I'm pulling now these out separately. I'm going back from the general notation to actually seeing what it means. And in that more general formulation, I would have epsilon squared there, except that remember that what that epsilon squared would mean is that actually it also has a curvature. It would depart in the x and epsilon direction, which would contradict this here. Okay. So I cross that out. So see the form of F and G, okay? Because that, again, that constant would just lift up the center manifold, right? And with X equals 0, Y equals 0 would have no more a chance to be a fixed point, okay? So, okay, so this is how I would then look for this. And I can just go ahead and, since epsilon is a constant, just work with the XY equations, because ultimately it's only X and Y. But the only difference is that I used to just look for center manifolds in this form, right? Now I'm including an additional term, which in this setting, in the XY setting, you would say, why am I including epsilon X in the XY setting? That's not quadratic. Yes, it's not quadratic in the XY setting, but I need to use the extended setting in which it is quadratic. So it's kind of an interesting newcomer here, right? When I look for the center manifold in this form. Technically, it's linear in the phase space variables, but since I'm using this extended setting, I have to consider it as a quadratic variable. And that's the most important takeaway message from this. Also, very often in tests or in calculations, this is the error that people make, that they don't include this because they thought it's just linear in X, right? And the center manifold must be quadratic in X. Not when you have an epsilon dependent center manifold. Then you're invoking a version of the center manifold theorem which mandates that even though you're still just working to find this guy, right? So ultimately in the XY space, you need to have that term there because that's your justification for the whole process to begin with. Other than that, the reduced dynamics is just the same, the way you compute it on this one slice. Okay. Now that slice still is, it's a general function of epsilon, so you'll be doing general work for M that works for any epsilon, but for the purposes of the actual computation, one has to think of epsilon as fixed. Okay, so then the reduced equation is the same story, that x dot is equal to ax plus fx. But when you see the y term, which is y tilde, you need to plug in this hx tilde that we were talking about here. So that will be hx epsilon, because ultimately what we're looking at here, when I rewrite it again, this is, and then I leave off the tilde, I think, from here. I can just think of it as a function of x and epsilon. Right? And that's what I'm writing here. And I'm plugging that in place of y. And I still have potentially epsilon dependence, high order dependence on epsilon in F, right? So that's not in Y. So this is in the spot of Y, the Y argument of F. And then this is the reduced order dynamics, like that. And this is what I'm after, the same way as I was after the reduced dynamics earlier. Now let's see how this works in practice. So this is again a calculation. I'd like to switch to the master set of nodes, and I'll copy these in. Yeah, see, I did in the master set of nodes, I did it better because I had more time to work on this. But I think this conveys better what I wanted to say. I worked on this for quite a bit, correcting the lines, but so this might be a better picture to use, but it conveys the same idea that you come in here with, finite slope. Here you come in with the tangency, and that kind of finite slope gradually evolves into what I have here, from the tangency. But other than that, it's the same deal. So let's look at this example that provoked the whole venture into center manifolds depending on parameters. So the example that got us to think about this was this perturbation of the original example, by which I just added this innocent looking linear term in epsilon, right? And it doesn't cause additional complication because it is of the form that preserves the xy equals 0, 0 equilibrium point, right? So also for epsilon bigger than 0. So when you look at this equation, this was the original linear part, which had the non-hyperbolic behavior, fixed point. This was their original quadratic part, and this is the newcomer, but that newcomer fits into the general form that I have assumed for F, right? Because it has this type of a term. So everything I've described so far applies directly. It's also, as you may remember, it was in the standard form to begin with. It was the linear part was block diagonal conveniently. Is the where's the linear part? The linear part. It had 0 linear part, and I had -1 here. So when I do the block diagonalization into A and B, right, then that was just 0, -1. That's why I wrote A is 0 and B is -1. We discussed this when we were talking about the problem without the perturbation. Here, this function fxy epsilon that I had in the formulation here, right? That function is simply what I have here, and that plus epsilon p is 1 here. The dimension of the parameters is 1. That plus the 0, the identically 0 function, that f and the 0 identically 0 function will be f tilde, and g just remains what it was, this one. So just using the machinery that I discussed, this slice that we're after, remember this was the slice, I can look for that for small enough epsilon. Epsilon, this is a limitation on epsilon, so this will not allow for you to do huge perturbations to the hyperbolic fiction and still proceed with this machinery. That's not going to work. Why? Well, I'm not just saying that, well, there'll be too much to ask for. No, that limitation comes from the center manifold theorem, because it's always just about a neighborhood in which you can guarantee this. And that neighborhood is now meant with respect to epsilon as well, from the epsilon equals 0 case, right? So it's only some neighborhood in the extended X epsilon place. So it's some small epsilon, we don't know. But here comes the upshot. I'm looking for y as a function of x and epsilon. And when I write out that function, I start with quadratic terms in epsilon. And normally, this is where the quadratic terms would end, because I would think of it only as a quadratic function of x. But now I have to think of it as a quadratic function of these two variables jointly. So then I have to talk about b times x epsilon, because this is now quadratic. C times epsilon squared I wrote here, but in fact, it must come. I just naively left it in there for the sort of pedagogical purposes, because if someone just remembers that I have to include all the terms. Remember, I crossed it out here to save some work for me, because for myself, because in the end it has to come out to be 0 anyway, because if it were not 0, it would violate the basic assumptions and the conclusions. But formally, you can certainly leave it there because it's a quadratic term. As I say, it must come out to be 0 in the end. And then I could go for cubic terms, but even when I take stock of the cubic terms, it's not just x anymore, but also these mixed terms, x squared epsilon, x epsilon squared, epsilon cubed. These are the cubic terms in the extended phase space, and then quartic terms, and so on. I'm not going to go for all those. I just wrote these out so that you get a sense of what it means to consider epsilon as a variable rather than just a parameter in this setting, so that it's in this setting, it plays the exact same role as x, because I'm using this extended version of the center manifold theorem. What doesn't change is that my basic helper is the invariance condition, right? And I don't have to write epsilon of t here, because at this point I know that epsilon is a parameter, okay? So the time dependence I will only have here, and epsilon is not going anywhere because epsilon dot is 0. So when I differentiate this relationship, I again take the Jacobian of h, right? Which these are the first few terms from there. And now I have a term which is linear in epsilon, because I took the Jacobian with respect to x. Luckily, I don't have to take the Jacobian with respect, with respect to epsilon. I could, but that will always be multiplied by epsilon dot, and epsilon dot is 0. So that's why I'm only getting away with taking the x Jacobians. And I'm only listing the leading order terms plus order 2. 2ax I had before. This is a new element here, that when I take the x Jacobian of this one, I get b epsilon. So that appears here. This is a difference relative to what I did when I was only analyzing this example. Other than that, it's similar. Now, what do I have? This, I need to multiply this by x dot. X dot is here, okay? And now imagine that y is a quadratic function and x is linear. So this is order 3 already. So I'm not writing it out because it's actually a higher order term. But epsilon x, I'm writing it out because it counts as a quadratic term. So it's lower in order. This is x dot from this differential equation. This is, and then when I multiply things out, it just gives me 2a epsilon x squared, b epsilon squared x plus quartic terms in x epsilon. The other way of writing it, this is how I get the invariance PDE, is that I work directly on the ODEs. I go back to the y equations, and when I see y, I plug in this enslavement relationship. So I have to plug in minus h till that, and that's all here, this lengthy expression up to order 4. Plus I have alpha times x squared, which was there anyway. And then, as in the case of the normal center manifold calculation, I need to equate these two. And then when I equate these two, these two can only be equal if term by term, the polynomials on each side are equal to each other. I have the order x squared here, okay? And again, here's the usual mistake. Oh, I have x squared here, I have x squared there, so I equate the two. Not quite, because you have to think of this as x to the second power and y to the 0th power, epsilon to the 0th power. And this is x to the second power, but epsilon to the first power. You cannot equate those two because epsilon is a variable now, okay? Think of it, epsilon in this context, as if it was y, in which case yx squared would not be equal to x squared, right? So you cannot equate those two. For that reason, you need to, then the only conclusion is that, well, I have an x squared on the right-hand side and I have no x squared on the left-hand side, okay? So I have to equate whatever I have on the right-hand side with 0 on the left-hand side. So what are the quadratic terms on the right-hand side? Not only this one, but actually that one too. So that's how you get that, whereas you get 0 from this one, you have to equate that in minus a plus alpha here, and that's what I've done. So that immediately gives a meaningful equation. It gives you a is equal to alpha. So then the next thing, again, you had to be cognizant of the fact that we're looking at equating powers of multinomials, right? Of epsilon and x. So the next term would be x epsilon. Do I have any x epsilon on the right-hand side? Yes, I have minus b times x epsilon, but nothing like that on the left-hand side at leading order. So that's why this is my next equation. Just gives me b is equal to 0. Similarly, here was that funny term, the order epsilon squared, and I told you that it must come out to be 0. In fact, that's the one thing I knew in advance. And indeed, you have order epsilon squared here, and nothing balances that, nothing on the left-hand side. So this has to drop out. C is 0, and that's why I had a tick mark there. That's the only thing I knew in advance. Okay, but it checks out as a consistency check. X cubed, again, I have d here, but nothing on this side. And if I had, you know, some epsilon times x cubed, I couldn't equate the two because those are two different monomials in the polynomial. Okay, so the only meaningful equation, the next one that comes in, is when I take stock of x squared epsilon, of which I have one here, okay, and I have another one there. And again, this is not a linear term. This is a cubic term. And I equate the two, I get this relationship. And then there's one more meaningful equation or non-trivial equation of this order, which is x epsilon squared. I have one of these x epsilon squared. I have one of these here. And I have, if all goes well, I have the j epsilon squared there. So I equate those two, okay? That gives me b equals minus, and so on, right? You get the idea. So then this is one equation, that's one equation. So if I stop here, then my equation for the center manifold is, I plug everything in, because what do I plug into? Well, my general form was here for h, right? In the leading order, when I plug those in, I get this, alpha times 1 minus 2 epsilon x squared. So it's quadratic in x as it should be in that well, that's how it comes out to be. At x equals 0, it continues to be tangent then in this case, and plus order fourth. So in this case, even when epsilon is non-zero, in this particular case, if I go back here, the tangency actually remains. That's what I get for this particular problem because it's simple. But generally speaking, I have to allow for this. And then I have, and this is a quadratic order, and the next one is order fourth, as it turns out, because I have all those zeros for the coefficients. So then I can calculate the reduced equation on this by taking this expression h tilde, and as said before, plug it into this equation. So whenever I see y, I plug in h, and then I leave that term as is. So that gives me this reduced order equation. Epsilon x now appears as a linear term, plus this is the nonlinear term at x cubed, and then higher order terms. And epsilon x now, the linear term, tells me about the stability. Okay, when epsilon is positive, and this is a positive, gives you positive growth, and when epsilon is, so then you get a saddle on this manifold, which is shaped like this. And then when epsilon is, for the appropriate sign of alpha, and then when epsilon is negative, you get stability, right? So it's the same type of analysis. Any questions on this calculation? So I'll include this in the notes, but I'll add them here. I want to, there's no questions, right? So I want to worry about another thing, which this is kind of the inconvenient truth, right? That I do this analysis. I want to scroll back here, but what really should be bothering to most of us is that there's this great tool, and then I have this invariant manifold here, which I know exists, and then obviously I'd like to understand what's happening on it because it's so important for the local dynamics. And I start doing that. At some point I truncate and I make this great prediction at least when alpha is positive, that I have two fixed points here, right? Remember that? Because when alpha is positive, then x equals 0 is a fixed, when I truncate here, right? X equals 0 is a fixed point, okay. And then I get 2 more fixed points here. And despite the fact that before even I went to do this analysis, I concluded very easily that this system has only one fixed point in the whole phase space, the underlying system. So I'm getting a false prediction from this highly involved analysis. Why is it a false prediction? There's nothing wrong with the underlying theory, but I made sort of an arbitrary choice that I truncated the reduced dynamics here. And that choice is justified when I'm really very close to the origin. But as I mentioned, these are points in finite distance. The coordinate is 1 over square root 2 alpha. Who's to say that what I'm ignoring is really smaller than this? Or even if it's half of it, you know, I can't just, that will have an impact even on the existence of that fixed point, because then it's just a finite size perturbation. Relatively speaking, this is a finite size perturbation on that. It's not an arbitrarily small perturbation anymore. I have it arbitrarily as a arbitrarily small perturbation near here, but not at a finite distance, right? So this is kind of must be bothersome, because then when do I know where to cut or where to stop? Obviously, I don't want to compute, you know, up to all orders. That's infinitely many. And after a while, it becomes questionable anyway, because the manifold is only CR minus 1, right? So we need to have some sort of way to address this. So the general question that I want to get to is, generally speaking, the effect of higher order terms in the reduced dynamics. And that really is a step towards more global analysis, because I'm no longer just concerned about the true stability of the origin, but I'm concerned about predictions I'm making about non-trivial behavior, nonlinear behavior nearby. Are these reliable or not? And this brings up to the next question, next topic, which is a very big topic in dynamical systems and still, you know, used and studied. It's it goes by the name of normal forms. And I explain that shortly. So before I actually say what it is, I will say that I used to do this in a whole lot more in general detail, but then it involves some really nice mathematics, but then also lose a lot of time with that. So I would say that for a general treatment of this subject, see Guggenheim and Holmes. They have a really nice chapter on this. So that's the book I recommended, Guggenheim and Holmes. And here, over the years, I just decided I'll end up doing only one example, a specific example rather than a general theory. So only a simple example. And of the idea, which is which is due to Poincaré, one of the big classic names in of the idea, and that's due to Poincaré. And it's all about addressing this question that I have just formulated. And before I define what a normal form is, I'll just more mathematically well, at least in terms of an example, the idea is the following. What is the question that I'm trying to see? What I'm trying to see is whether the truncated reduced form, reduced dynamics, already captures the full dynamics close to the origin. What does it mean captures? Is it going to be identical to the full dynamics? No, because there are more terms there, right? So clearly the two differential equations, the truncated one and the full one, even on the center manifold, they're not the same. So when I say captures, what do I mean? Let's be a bit more precise. We have a notion of equivalency between dynamics of truncated or simplified systems and the full system. We talked about that when we talked about the relevance of linearization for the full nonlinear problem. It was very much the same question, except that there I stopped at linear order and I was trying to relate my conclusions at linear order to the full nonlinear system. What I'm doing now is that on the center manifold, I'm not stopping at linear order because then that's inconclusive, right? That's why I'm doing the whole thing, because linearization is inconclusive. So I'm actually including now some nonlinear terms as well. And then I stop maybe after cubic order. And it's the exact same question again, that after stopping at cubic order, is that are the dynamics related to the full system? So once we realize that it's the same question, then the mathematical intelligent formulation of this question is the truncated leading order reduced dynamics on the center manifold topologically conjugate to the full dynamics on the center manifold. That's a proper way of phrasing it. Remember the term topologically conjugate? It means, is there a homeomorphism, a change of coordinates, which is at least continuous in both directions, invertible and continuous, that would take this truncated system to the full system. And then all of a sudden, this sounds like a mathematical question, right? And that's exactly what Poincaré was looking at. He said, let's look at problematic fixed points. Let's assume that I have to include more than just the linearization, a few more terms. Happily, I'm seeing some non-trivial behavior. I cut this system right there. I analyze it. Now, can I say that this system is topologically conjugate to the full system, which means not one-to-one relationship, but continuous deformations of the phase space of what I'm getting would take me to the full system, right? So they're due to Poincaré, and the idea would be, if possible, find topological conjugacy between the truncated normal form not truncated, sorry, I'm skipping ahead, truncated reduced dynamics and full dynamics on the center manifold. Okay, that's his idea. So what's a topological conjugacy? Find a change of coordinates that would relate, that one would map one into the other. Okay, and one motivating example, before I even do that, and probably this is what I have time for, of the types of things that we would like to better understand with such an approach. This is example 5. Maybe I have some time to do this quickly. So this is the specific example for which I will try to do this exercise, rather than the whole approach works in many dimensions, even in some cases in infinite dimensions. But I'm just going to do a one-dimensional example. So I'm imagining that I have this type of a reduced leading order equation on the center manifold, because that's exactly what I've seen here. Where was that little example? Look, it's sort of the simplified version, and even simpler than this, right? So I had a power of x here, which is cubic, multiplying this factor, which was 1 minus x squared, right? And constant times x squared. Okay, so I don't necessarily have to have the cubic power there. Let's just have a lower power there for simplicity. And I'm going to worry whether this thing here, which is predicting me one type of dynamics already, sufficient, or must I add higher order terms to really understand the full dynamics? Now, why is this a good example here that I'm writing out? Even I would then add the higher order terms like x to the 4th. But that's sort of the question, that this is my truncating leading order dynamics on the center manifold. I'm ignoring things, but should I include them? Or should I possibly even go for higher order if I want something that is topologically conjugate to the full dynamics on the center manifold? Now, is this simplification okay? Does it reflect the fact that I have non-hyperbolic dynamics for the fixed point at the origin? Yes. In the context of center manifolds, depending on parameters, yes, because then I think of mu as a one-dimensional parameter whose known. Think of mu as the epsilon. I changed to mu because in this setting, it's just customary in what I'm going to do. And for mu equals 0, you have a non-hyperbolic fixed point, right? Because when mu is out, this is x cubed. So that means that the linearization is not really giving you anything. But using a center manifold depending on parameters approach, like this one, this is what we were getting. Except I need the pointer, right? A linear term in multiplying x, so this is like mu times x, plus a quadratic term in x, and then potentially higher order terms. Well, generally speaking, higher order terms. So when I look at the center manifolds depending on parameters setting, then we've already seen this, right? That's why it makes sense. I'm getting mixed up between the two. So again, that would be the cubic term, and then when I add that parameter, I'm tuning myself away with that little perturbation from the hyperbolicity. And I say to myself, okay, you're not just confined to the non-hyperbolic limit, you're really taking care of extending it in mu, and you're even, but then should you stop here, or can you add that, or once you've added that, should you stop there, or go to higher order terms? So what this would be is that what this models is one of the most frequent examples that you would see as reduced dynamics. In fact, generically, this is what you see on 1D center manifolds. Depending on this parameter. In this setting, epsilon is just mu. Okay, and very quickly, we can analyze this system. So I'm thinking of this as the rest is cut off. And we can analyze this system very quickly by noting where its fixed points are. So the fixed points are at x equals 0, no question, right? It stays there always. So that's 1. But I can get 0 on the right-hand side also by factoring out x and making the rest 0. Right? So when I factor out x, then I get x cubed here, right? So I would have to then solve this equation. So I need to look for zeros of the function g mu x equals mu minus x squared plus x cubed equals 0. That's what defines my fixed points. And then quickly, probably I can just sketch this quickly and then talk about it in more detail next time. But these equations define my zeros. And what I'll show here is these zeros as a function of the parameter mu, which is one-dimensional. So basically, this is always a 0. So if this is mu, and in the other direction, I plot x for the fixed point, so it will be x0, this is the fixed point. Then in the dynamics always takes place in these little one-dimensional phase spaces, because the equation that I'm looking at is fundamentally one-dimensional. So it's always confined to a copy of the x phase space, right? It's a one-dimensional equation. But that the dynamics in these one-dimensional phase spaces will be a function of mu. And what I conclude before doing much work is that this is always an equilibrium point. And that equilibrium point, so this is mu, I have the 0 here. That equilibrium point is in fact stable for mu less than 0, because just look at this equation here. This is the linear term. When mu is less than or equal to 0, or less than 0, I have minus mu x. So my eigenvalue on the linearization is minus mu. So surely this is a stable fixed point. So in all these slices, I'll have decaying dynamics, no matter what. Okay. And by the same token, when I switch mu to the positive domain, then that same fixed point, which is still a fixed point, becomes unstable. So all of a sudden, I'm moving away from the origin. And there will be another branch of equilibria, which is simply defined by this equation, which I can rewrite as mu equals x squared minus x cubed, right? And along that curve, the right-hand side is 0 again. And I can plot that curve. I view mu as a function of x, and I see that's near the origin. That's like an inverted parabola, like that. And then for positive x values, it goes down, and for negative x values, it goes up. So these are the negative x values, right? So it goes up this, and it goes in the other direction. So let me just quickly draw that. Well, I'll do that next time. So basically, this is what we're looking at, another branch. This will be called a bifurcation diagram because it tells you how equilibria of the system change as a function of the parameter, and we'll be discussing that. And we'll be trying to see how much I need to include from the equation to capture various features of that, and whether higher order terms, when I add them, would change that curve. But I'll stop now because I'm out of time. Any questions? So just one correction here is that I'll call this x naught, because that's what I call the fixed point, x naught. And all the way I should be using x naught here, because this defines it. X naught is the fixed point, and these are the equations defining it. It's kind of a funny thing that I write as mu is a function of the fixed point. The fixed point is a function of mu, but in this way, it's easier to plot this curve. Mu is a function of the fixed point. Okay, anything else to discuss today? Are we done? Okay, that's it for today. Have a good rest of the week. See you next week. Have a good day.